So good morning, good afternoon, everyone. Thank you very much for joining the webinar today. So we start the new year, academic year 2022-2023, for our TAES webinar series on data science in environmental applications. And I'm extremely thrilled to introduce Sudipto Banerjee from University of California, Los Angeles, who has been member of TAES for many years and who has been involved in the different TAES activities for many years, including being Abdel El Sharawi Young Investigator Awardee. And Ignacio will provide more details about Sudipto, but just as a vice president, I'd like to say that we are very excited to have Sudipto here today. Thank you.
Thank you, Julia. This session consists of 40 to 45 minutes presentation and 10 to 15 minutes for questions and answers. We suggest attendees to ask questions at the end of the presentation. And as Julia mentioned, we are so glad to present our today's speakers in this TAES webinar series on data science for environmental sciences. Sudipto Banerjee is a distinguished professor and chair in the Department of Biostatistics and affiliate professor in the Institute of the Environment and Sustainability, both at UCLA. He has a PhD in statistics from the University of Connecticut, had wrote numerous articles on spatial statistics, developing theory and methods related to Bayesian modeling and inference for geographic data, with wide-ranging applications in public and environmental health sciences, real estate economics, and ecology. Banerjee has received many honors, including the Abdel El Sharawi Award from the International Environmental Society, the Mortimer Award from the American Public Health Association, and the George W. Award from the Committee of Presidents of Statistical Societies. His papers has thousands of citations and has collaborations with dozens of scientists all around the world. Dear Sudipto, thank you so much for accepting our invitation and making time out of your busy schedule, and welcome.
Well, thank you very much. Can everyone hear me? I hope. Yes. Okay, thank you so much. First of all, thank you very much for these very generous and kind remarks. I indeed have been associated with TAES for a very long time. I would say definitely over 20 years. In fact, it was one of the first professional societies for which I became a full-time member. And of course, that was no surprise because TAES has always been, the activities of TAES has always been very central to the advancement of what nowadays people refer to as spatial data science. When I was in my formative years as a researcher in spatial statistics, the term data science was not used as much, but nowadays folks use it a lot. And I suppose the reasons are not completely unjustified, because data science encompasses a lot of features, including the processing and compilation of spatial data, which sometimes is done better by computer engineers and GIS programmers than by statisticians. So I am definitely not someone who believes that data science is equal to statistics and vice versa. I would say that statistics plays a very important role in data science. And of course, spatial statistics plays a very important role in spatial data science. And I would say that it provides or offers the inferential component, the uncertainty quantification component, the understanding of variability component. And so with that being taken care of, I'm going to just give you a brief overview of how I'm going to present this talk. This is not going to be a talk that will basically focus on one particular method and go deep into that. I'll try to borrow a lot of stuff from some of the work that I have done over the last, I would say, 6, 7, 8, maybe 9 years, with a lot of very high energy and extremely gifted collaborators with whom I have been very fortunate to work. Some of them are TIES members as well. And also I'm going to focus mostly on the geostatistical framework, which basically means spatially indexed data where the indexing is with respect to point locations. That's not the only type of spatial data, but in high dimensional problems, I think that is the one that presents the more pressing challenges. And I'll try to provide ideas, I'll talk about them, and then hopefully many of you who are starting your research career will start asking questions and perhaps think that some of these methods can actually be expanded, improved, and certainly take on new research problems. Okay, so just to give you a very quick example, this is a data set from the beautiful state of Alaska. And by the way, these slides I have sent to Julia and Ignatius, and they can distribute it, and you can feel free to use it in any way you like. These links, I've tried to make them clickable. So if you click on these references, you will get to the paper and you will be able to see the details of the analysis as well. But basically, this paper appeared in JCGS in 2019, and we analyzed a data set that was coming from the Tanana Valley in Alaska. So here you see the state of Alaska, and Tanana Valley is this part right here. And these red lines that you see are LiDAR flight paths, right? So LiDAR is a remote sensing technology where basically you have an aerial instrument, so to speak, which is more likely to be a drone, and that actually takes high resolution images as it flies over a region, and the data keeps coming. So what happens here is that, there is a chat message. If the link can be provided in the chat. I don't know exactly how to do that right now, but what I will try to do is perhaps, if you get a hold of the slides from Ignatius, you will be able to click on that and just get to the website.
Yeah, we can distribute this via our website. So no
Thank you so much. Yeah, and so you have these high resolution images that are coming in about forest height, and from that you actually develop research questions and try to answer them in appropriate ways using statistical methods. So one of the main goals of this specific study was to actually provide high resolution domain-wide prediction maps for forest height, and you're trying to understand the height of forests in the context of perhaps certain external disturbances. For example, like forest fire within the last 20 years. So here, for example, you see these LiDAR flight paths here, and you see this grayscale plot where the dark grays represent the percentage of canopy cover in that particular pixel or that location on this in this map. And you have, for example, the forest fire history, as is seen here in these red regions, where this is more like a binary data, 1 or 0, and saying whether that particular location had been affected by a forest fire within the last 20 years or not. And foresters are often interested in trying to understand if forest height, in fact, can be predicted or explained well with these sorts of explanatory variables, such as percentage of canopy coverage at the current time, as well as historical disturbances of forest fire for the last 20 years. So keeping things very simple, before you invest in spatial modeling, which by the way is computationally very expensive, one of the first things you like to do is to simply do a simple linear regression. And if with this information, let's say you don't want to invest in spatial statistics without trying to see if there is enough structure there, you could take your forest height variable as a continuous variable, for example, at a location, and then you simply use a ordinary least squares type of linear regression and intercept here the canopy, percentage canopy as a covariate here, which is a continuous covariate, and then x fire here represents a 0-1 binary variable representing whether there was a fire at that location or not, and then you try to do this linear regression. When you get the residuals from this regression, you could pass this through a variogram function, and the variogram is one of the most widely used exploratory spatial tools available. And basically what it does is it actually gives you an empirical estimate of the variability among neighboring regions, essentially. So it looks at more precisely as the variance of the difference in the outcome or the variable that you're looking at, or maybe the residual in this case, as at a location L and at its neighboring locations. And you try to look at the variance and you plot it. And so basically this is an empirical plot. You see these dots, and they have been fitted using a weighted least square with a exponential variogram. But the important thing to look at here is this particular pattern, and to see if spatial modeling is worth the trouble. So here, if you see there are 3 lines here, 2 horizontal lines, one around 11 and another a little lower than 20, and 1 vertical line. The lower line here gives you an eyeball estimate of what is called the variance of the residual, or the nugget, as we like to call it in spatial statistics. And that's basically the variance of epsilon. The top horizontal line, which is around 18 or 19 here, gives you the total variability in the data. And then this particular vertical line, it gives you the effective range. So that means it's the distance beyond which you expect spatial correlation to be dropping to 0. And so if you get this very clearly, as we have in this particular data set, then you really think that, there's enough spatial structure in the residual to try to, invest in a spatial process model. And perhaps you will really get some benefits out of your predictive performance or your inference. Okay, so you want to do this, okay? Now, one of the immediate problems, even before doing spatial statistics, if you want to actually, let's say, just fit a linear regression, this could be a little bit of a problem, because one important point here is that there are about 40 million locations right here from the LiDAR data. 40 million, okay? And 40 million is pretty big. I mean, you cannot even in more than modest computing architectures, even storing the data, and particularly not in the CPU storage, but more like in the random access memory storage, where your program will need to access the data, it's going to be a problem. And I believe in your laptop, if you want to do this using R, you will not be able to do it, because it will just say that I don't have enough memory to do it, to do any computing. So before even getting to more complicated models, even if you want to actually run a linear regression on a very, very large data set, you need to probably spend a little bit of time in trying to figure out how to do that. And this is where I think, our training in statistics is important. And this is not just a computer science problem of getting bigger and bigger machines, because you can actually use some distribution theory to actually make this work even on a very, very modest computing architecture. So for example, since I like to do things within the Bayesian paradigm, let's suppose you want to fit a Bayesian hierarchical linear model to that data set, okay? So each unit, again, no spatial structure right now. Each unit yi, conditional on beta and sigma square, will be assumed to follow a normal distribution with the regression component. and let's say a variance of the noise, sigma squared, and this is for each unit n. N here is 40 million, okay? Just keep that in mind. And then in order to get to tractable distribution theory, I will develop a hierarchical prior with beta conditional on sigma squared. So it's a normal with a scaled variance. So sigma squared is the variance term and V beta is the prior correlation matrix for beta. And then sigma squared itself follows a inverse gamma distribution. If you do this, then you can work out the distribution theory and you can actually get exact Bayesian inference. You don't need to do any MCMC or anything. This is all tractable analytically. And so you would have sigma squared given y will follow an inverse gamma, and beta given sigma squared and y will follow a multivariate normal. I like to call this the M&M formula when I teach it, where lowercase m is computed like this, as you see here, using these parameters, v beta, mu beta, y, the vector y of the entire data, n by 1, and x transpose. And then m inverse is given like this. A star is this, and B star is this. Okay. Now, by the way, the marginal posterior beta, which is if you integrate out the sigma squared from the conditional posterior here with respect to sigma squared given y, is in fact going to be a multivariate T distribution. So all of this is in fact analytically available, but usually we do sampling based inference. So we will first sample from the marginal of sigma squared given y, and then for that drawn value of sigma squared, we'll draw one instance of beta, and that way we'll get samples from the joint. Of course, the question is, if this cannot be stored or loaded into the available workspace, then how am I going to even compute this guy? Because there's an x transpose y here, and then there's this x transpose x. So, you know, it immediately, completely naively, this may not fit into your workspace, your computational workspace. So there are these different types of frameworks, very sophisticated ones like Hadoop that actually work well with divide and conquer, but you don't even need that much. What you want to do is simply work out a little bit of math, and you can basically see how you can in fact split the data into subsets, partition them. Don't throw away any of the data, but take subsets, like maybe the first few rows and the next few rows and the next few rows. And then there are two options for you to pursue. So now, you know, you have, I'm replacing this lowercase n here with the uppercase n, so that I know that this uppercase n is now 40 million, but each of these lowercase nks, which is the size of dk, this data set, is going to be manageable depending upon how much storage you have. You can take it 20,000, 30,000, 100,000, depending upon how much you can manage. But then, you know, there are two ways you can work this out. One is like sequential update. So take each data sequentially, and the beauty of Bayesian learning is that you can keep updating. So probability of beta given beta and sigma squared, given all these data sets from 1 to k plus 1, you can update from the posterior based upon the first k data sets, and then the likelihood of the k plus 1 data set given beta and sigma squared. So as you can see, you know, if you go one by one, each data set is small. So you're going to start with V1. That's a small manageable data set because that's how you have actually done that. You get the posterior, then get to the second data set. At no point am I actually working with the whole data set, and therefore I'm only working with the size of the subsets at each step. And so I can certainly do that. So it will just be calling the part of the data wherever that data set is stored, perhaps in a cloud or something. Even though it is huge, I only need to take the subsets and just keep the sequential updating. Another approach, which is exactly equivalent, by the way, this by the way is going to essentially provide you with the same inference that you would get from the big data set, the whole data set. I'm not throwing away anything. It's just the way I'm updating it that is a little specific. Then you actually go to a different way of updating, which is a parallel architecture scheme. And so you can compute simultaneously. And now all you do is simply do a little bit of linear algebra to simplify the M inverse and the M in the following way. You know, you can take for each data set the MK and the uppercase MK inverse, and they're all NK by NK, which is manageable. and then you can recover the M&M here for the whole data set by simply these linear operators. And they don't need, again, any big storage or any expensive computation. So in other words, if you actually are careful enough to take a simple enough tractable model, you can actually analyze big data, no matter how big it is, using these different types of techniques. One point I do want to emphasize, which is where nowadays we encourage students and emerging scholars to learn algorithms and computing, is that even though these two methods are equivalent, the type of computer architecture on which you are going to operate could actually provide a preference or suggest a preference of one to the other. So for example, if you are in a very straightforward vectorized linear architecture, then the first method is fine. It may be a little slow, but if you do have parallel architectures, especially in the form of Hadoop, then doing this computation simultaneously could be far more efficient. No matter what you do, the important thing is mathematically, you are able to do this exact inference on this entire data set, fitting this entire model without working with the entire data set. Now, of course, this is a very simple toy example, but this is one of my first examples that I teach when I teach a big data class with linear regression and Bayesian linear regression, a little bit more complicated than the usual classical linear regression. In the classical linear regression, the V beta inverse will be 0. So all you will have is just xk transpose xk and xk transpose yk, and you can easily do that even simpler. So it's not a problem. Bayesian, because of the priors and so on, you also have this option that you can use. Okay, now this of course depends very crucially on the independence across the subsets, because the entire data set is each unit is independent. You would have that. Now you could actually relax this assumption in certain cases, perhaps do block independence of certain types. If you think your spatial structure is such that a block independence approximation is going to be fine, meaning that within the block you have correlations, but between blocks you have independence, you could still do this. But once you want to actually go to trying to estimate an entire spatial random field where everything is correlated, then this is going to break down. Okay, so in other words, if I now expand my model, having looked at the variogram here and deciding that there is enough spatial structure for me to introduce a geostatistical model where I bring in a spatially point reference process, which I call W of L, into the structure, and this W of L could be a spatial process. Most widely uses the Gaussian process because of its tractability. And you could actually use that as a prior on this process. Well, fine. In that case, your entire vector of observations follows a big multivariate normal. X beta, k theta is the matrix, the variance covariance matrix, and it takes the form of something like this: a C of sigma phi, which comes from the covariance function that is into the Gaussian process. And then you have a tau squared I. This tau squared comes from the nugget. So in other words, the parameters besides the regression coefficients in this model that determine the process or the likelihood is in fact the sigma, which is a spatial variance component, the phi, which is the effective range or a decay parameter, depending upon how you have parameterized your covariance function, and then the nugget variance. So if you go back to the picture of the variogram, the tau is this guy, this estimate here, this horizontal line. The sigma is the difference between the top horizontal line and the lower horizontal line. And the range is given by this vertical line here, the phi. Okay, so those are the three. That's how these correspond to the variogram. And so there are many different questions that you may be asking yourself. Okay, all this is great. I like spatial structure. I want to actually be able to predict at a new location, taking into account the fact that nearby locations could be correlated, which definitely makes a big improvement in predictive inference over assuming everything is independent. That's one of the main reasons why we invest in these models. But then the question is, how am I going to fit this? Because I'm talking about 40 million locations, and 40 million locations means that the C matrix and hence this K matrix is 40 million by 40 million. And interestingly, there's a very rich literature in theoretical spatial statistics about different classes of these covariance functions. And certain covariance functions actually have been established to perform better predictive or deliver better predictive inference than others. And interestingly, the ones with the richer theoretical properties do not necessarily render sparse or exploitable structure for the K theta by themselves, so that we can use scalable algorithms. So that's the problem. Okay. Now, let's look at this thing. So what about divide and conquer? Well, sure. But as I said, there is this issue that this block independence is not there. So it won't work like a vanilla way. How about Bayesian model averaging, predictive stacking, exchangeability? All these are open questions, and none of this has really been explored in great detail. The divide and conquer, though, has been kind of tackled by us in an earlier paper that appeared in Technometrics in 2018. Again, you can click and get to the paper here with my former student Raj Gohniyogi, who's now in Texas A&M University. And basically the idea was, okay, fine, we'll take these subsets, we'll calculate the posteriors for each of these subsets, and then we'll try to use a functional median of the posteriors to try to get to a best meta posterior of sorts. So it is a little bit like meta-analysis of spatial statistics, but obviously because we are working with Gaussian processes, stochastic processes, which are a little more complicated than distributions, we will actually need to work this out a little bit differently. So I'm not going to get into the details of this. The one problem I would say, or perhaps a limitation of this method, is it's much more algorithmic in the way it combines these subset of posteriors than anything else. So now you analyze this compressed data, compressive sensing, data sketching. That's also another way of doing it. You could actually just simply pre-multiply this vector by a short, wide, random matrix, and that will lead you to a compressed data set and just work on that compressed data. But again, you lose some structure, and it's not as simple or not as perhaps effective always to work with these machine learning based methods for spatial data as a fully model-based approach could be. So, but I encourage you to think about these problems as you embark upon your research careers, for those of you who are doing so. Now, in terms of the paradigm, the way we like to think about this is that you have the data and you want to have a probability law for the data given the process and the parameters. Then you come to the process given the parameters, and then as a Bayesian, you go with the parameters. If you're a frequentist, or if you're a non-Bayesian multi-level or hierarchical modeler, then you would perhaps stop here and you don't bother about the parameters. But for us, it's about probability of the unknown given the known. So parameters are unknown, random effects are unknown, you haven't observed them, there's no study designed to observe them really, and so therefore you want to make probabilistic inference about such quantities. So you look at the prior on these parameters. So here's how you look at it. So you can go with the parameters right here. Then you go with the process given the parameters. Then you look at the process at arbitrary points given the process at observed location. So this is W is the process at observed location, still unknown, random effect values at the observed locations. Then you have random effects at unobserved locations, and then you have the likelihood, and then you have the predictive random variable, or the value of the outcome at the unobserved locations, and you could give us any. And so this gives you the entire joint model. So the posterior predictive inference usually follows like this. You have the posterior over the observed data and hence the observed locations. Then you go to the posterior or the conditional posterior of the random effects at the unobserved locations, given, and this given everything else is still going to boil down through conditional independence on the value of the process at the observed locations and the process parameters. And then you get to the predictive random variable again. Given everything else, it will only be depending on the values of the W tilde and the theta and the tau. Multivariate examples can be done. So for example, this is just one example. Instead of looking at multivariate normals, you can look at matrix variate normals. So where you can actually arrange your data as a matrix, as a random matrix, and then you can assign a matrix variate normal distribution on the y given x beta, a covariance matrix, and a variance covariance matrix among the variables. Then you could do a matrix normal on the b's, and then you look at the inverse Wishart, and then you could look at the priors. And you look at the, okay, so now here comes, so I want to come to the next segment here, and I need to speed up a little bit. I've been talking too much, having too much fun here, it seems. But one question is, in these sorts of paradigms, okay, this is the part, the process model here, this guy right here, okay, is the one that creates a computational bottleneck, frankly speaking. Because if you have this in a particular way, then even this is in fact going to work out well. If you have this in a scalable way, then this could also be scalable. So the question is, what can we do? And I'm going to focus for the next 10 minutes or so on this approach for graphical models. So if you look at the joint distribution of all the random effects, and let's say here you have 7, and 7 is very large for you. Well, you can factorize the joint distribution using your Stat 101 joint or compound probability model, right? W1, W2 given W1, W3 given everything else, and so on. In the language of graphical modeling, this is known as a DAG, directed acyclic graph. In Bayesians often like to refer to these as Bayesian networks as well. But basically, it goes like this. You can represent this like a DAG. So the graph will have the locations as the nodes, and then you will go ahead and just label arbitrarily or number them as 1 through 7, and then simply create the DAG. So you will have a pointed arrow from one node to the next if the child, which is the one where the arrow ends, is dependent on the parent, which is where the arrow starts. All right. So that's how a DAG is constructed. And the easiest way to build a sparse model from a DAG is basically to take a nearest neighbor. So in other words, just assume from here that beyond a certain point, okay, I'm going to, let's say, just look at 3 nearest neighbors. So I come up to W4 with its 3 preceding neighbors, W1, W2, W3, but I'm going to choose from then on the neighbors from the conditioning set that are closest to W5, and I'll fix the number of neighbors at 3. So W5 given W1 through W4, so 5 is here. Euclidean distance wise, 2, 3, and 4 are much closer to 5 than 1. So I just retain 2, 3, and 4 and get rid of 1. When I come to W6, I see that 1, 4, and 5 in terms of Euclidean distance are the closest to W6 from the past. Okay, no, I don't consider 7. 7 is clearly close, but 7 will come later in the sequence. So I just retain 1, 4, and 5. And then finally with 7, I retain 1, 2, and 6, which are the 3 closest neighbors. So that's how you actually can build a sparser graph, and that leads you to a sparser likelihood. I'm not going to get into the details of this, but what this does really nicely is that it leads to a very nice exploitable structure for the precision matrix. I'll show that to you in a second. But there are 2 papers and 2 associated R packages coming from my collaborators with whom I'm very blessed to have been working. And one of them came from out of the dissertation of Abhi Datta, who's himself a well-established biostatistician now at Johns Hopkins. It's on the NNGP, or the hierarchical nearest neighbor Gaussian process. And then with the former postdoctoral fellow of mine, Michael Peruzzi, we actually worked with modification of this for meshed Gaussian processes. And both of these have associated R packages that you can try to explore. One is called meshed, and the other is called SPNNGP. Again, these are clickable. They will take you to the CRAN website for downloads. The papers themselves are also available from the journal's website. The one connection I just want to point out, the basic idea is that if you look at this whole idea about big spatial data, one thing you can try to do is try to connect it to dynamic modeling, where there is a lot of work to make it scalable. And the idea is not completely dissimilar. So you can have a spatial model, Y of S, XS transpose beta, plus maybe some design matrix ZS times WS plus epsilon S. Okay, so WS is your spatial effects. These could be all be vectors or scalars, depending upon the dimension of the Ys and X's and Z's and so on. And then you could have a transition for the multivariate spatial process, if this is multivariate or univariate, as it depending upon what you have. And you could have a linear combination based upon the W, except that the W is not over everything else, but only on the parents of S that come from a graph that you decide to work with. And then, you adjust with 2 different disturbances, one at the measurement level, which is more like white noise, and the other as eta S, which itself could have some correlation structure. And this can be connected to linear Kalman filters or state space models. And you could even modify your usual Gibbs sampler to more efficient Gibbs samplers, such as the forward filter, backward sampling Gibbs samplers that usually work well with these sorts of models. And then there are some other types of very nice papers that have come out. For example, here's another link to a paper which looks at marginalized factor models using state space modeling frameworks and so on. The structure from a DAG, when you impose that DAG to the covariance matrix, is that the precision matrix becomes analytically tractable up to the Cholesky factor. And you can essentially look at the sparsity. It becomes sparse. And not only sparse, you can get this A and the D in closed form. The determinant can actually be computed. The A matrix is the lower triangle. The I minus A's can be looked upon as a triangular factor of the Cholesky for this. And you can in fact calculate the elements of the A matrix also very, very efficiently. The details you can find in that paper in the first slide on the Tanana value. So I'm not providing that, but the whole idea of this DAG comes from a very well-cited paper by Vikia in 1987. The paper was somewhat dormant in terms of attracting interest through the 90s, although some people did work on that, but it really got a rejuvenation of citations since the 2015-16 with NNGPs and graphical Gaussian processes and so on and so forth. Lots of work from our group, as well as many other groups, have worked on this approximation to build scalable models. I'm going to just very quickly go through this because the details of this are available. One thing that you can do is you can get to conjugate spatial models where you can do MCMC-free inference. And the idea is to actually fix certain parameters, such as some functions of these guys, like the noise to signal ratio and perhaps a range parameter from the variogram, and then do some distribution theory to get exact closed form analytic formulations. And that way you can actually analyze a 40 million data set in reasonable time. In this particular setting, this example, this particular table comes from 5 million locations And I did this only on my laptop, which is a very, very standard laptop. And a conjugate model will just take about 7 seconds for giving you the inference. If you want to do more conventional Gibbs sampling, then you can do different types of algorithms. Again, they're all detailed in this JCGS paper, all MCMCs, but different variants. So like you could do a collapsed NNGP where you work with the collapse likelihood, integrating out the spatial random effects to work on a reduced parameter space, or you could model the response itself as an NNGP. And these all have different computation times. So you could look at these as well. If you have a very large number of variables at each location, which is an area we are gradually coming into, then you have a high dimensional spatial model where not only perhaps the number of locations are big, but the number of variables are also quite large. And then how can we do that? Now, this actually also is in fact gaining a lot of traction in recent times. And the original approach for multivariate spatial processes, follow from different perspectives. One is a conditional modeling approach. Another is a joint modeling approach using the linear model of co-regionalization. There is a pretty big literature on that, which basically is like a factor model, where a factor model basically reduces the number of latent processes, whereas a linear model of co-regionalization keeps the same number of latent processes as the number of variables that you have. So the idea is essentially that if you have Q variables, and Q could be pretty large, then for each variable you construct a model such as this. Here comes the regression component for that variable. J is the variable now, right, at each location. And then J indexes a variable. And then you have a kind of a factor loading coefficient and a latent factor, which is a spatial process itself. And then you have the noise. And you can work this out using a matrix normal distribution like this. X beta, plus you collect the Fs into an N by R matrix. The factor loadings become a R by Q matrix. And then you can build a conjugate, efficient, scalable model by looking at beta given sigma as a matrix normal, the lambda given sigma being a matrix normal. This sigma you can retain to be the same for computational efficiency. It will basically represent the association among the variables here. Put a prior on the sigma as inverse Wishart to get conjugacy. And then for the F, this will be a realization of these guys, the F sub J's. Each of these guys could be modeled using your favorite scalable GP. My favorite one is perhaps going to be one of those Vecchia-based approximations like the NNGP or the mesh, but you can choose any that you like. And that, in fact, can work out. In fact, more flexible options are available, and you could even do a matrix normal. You can go beyond the matrix normal distribution as well. Okay, so that's basically the extension of traditional conventional spatial factor models or rather I should say traditional conventional factor models into spatial domains. Okay, to get spatial factor models, all you do is take the traditional factor models and then simply replace the factors with latent spatial processes, still a smaller number of them, so that you get the dimension reduction. A completely different approach it comes when you have a very large number of variables to model at each location, but you also now have a scientifically posited graph that tells you about the relationship among those variables. So the factor model doesn't really give you a lot of structure about how these yj sub s's across j are associated. Okay, but perhaps you have a graph that is given. And they come from these conditional independence graphs. There's a beautiful book by Cox and Wormuth that talks about this, Multivariate Dependencies. You can read about it there. And there are, broadly speaking, two types of graphs. One are these directed graphs, where you have directed arrows, very much like the DAGs, as I showed you. The other are these undirected graphs. So the idea here, the DAG I already talked about, the idea here is that in the undirected graph, if you have two nodes which do not have an edge between them, then that means that those two nodes, or the variables corresponding to those nodes, are conditionally independent given everything else. Okay, so for example, 1 and 4, that means y1 and y4 are conditionally independent with each other given 2, 3, 5, 6, and 7. All right. Whereas in the directed graph, remember, it goes sequentially. So you are conditionally independent only based on your past. And there is a very rich literature about how the two types of these graphical models relate. One is a special case of the other. In particular, for example, if you notice this guy, if you have a directed graph, you can always get a moralized graph, undirected graph that will retain the full conditional independence relationships posited by the directed graph. So basically, the full conditional posited relationships here are retained here. What have I done? I have simply wedded the unwedded nodes. That means the non-adjacent nodes when they have a common child. So for example, 2 and 3, they both have 5 as an offspring. So we add an edge between 2 and 3 in the undirected case and then remove the arrows. You can look at Wikipedia for graphs or directed and undirected graphs. Very nice explanations are provided there. How can we now use a given graph that a scientist has provided us with in our multivariate modeling? Okay. And so here things start getting a little bit technical, and I'm going to run out of time. So I'm going to just go a little bit quickly here. So let us suppose I look at each node and build a conditional auto-regression, like a linear regression, conditional on everything else, using something like this. Okay, we love linearity, so make this a linear combination of everything else. So CII is going to be 0 because you can't have a WI here. And then the CIJs are all 0 if I and J do not belong to the set of edges on the given graph. Okay, if I give you a set of these conditional relationships, do they imply a joint distribution? Under broad regularity conditions, the answer is yes. I'm not getting into those conditions, but there is a very nice lemma, very easy to prove in one line, essentially, that basically says that the joint distribution will be proportional to the product of these ratios. And these W tildes are simply arbitrary values that you can put in. 0, for example, in the case of the normal, because it's in the support of that distribution. 0 is in the support of the normal. And then you get essentially a form like this, and the Q turns out to be fairly tractable like this, with M being a block diagonal matrix whose block diagonals are these gamma i's, and the C here is a partition matrix with the blockCij's here. Then you can put in some conditions where Q must be symmetric and positive definite. The most common version of this in aerial modeling coming out of this or emerging from this framework is the conditional autoregression models or the CAR models. But we are not going to look at the CAR. What we are going to try to look at is a slightly more general way to construct multivariate models out of processes. That means, what about where each node, in fact, is a Gaussian process in itself, not just a random variable or not even a vector of random variables, but an uncountable set of random variables. That's what a process is. Okay, that's what you need to model when you have to relate processes. Well, we can look very similar to the CAR models, for those of you who are familiar with it, to the precision of the CAR, which is like the graph Laplacian. So you have a diagonal matrix, you have the adjacency matrix, and you have an autocorrelation parameter that essentially can be constrained within the eigenvalues of a compressed adjacency matrix to try to see or make sure that the Laplacian is always positive definite. Then, what we can do is we can construct a joint distribution out of processes. Take the variance covariance matrices that could come out of a conditional of a cross covariance or covariance function, and look at the realization basically. So those are the gamma i's, and then look at the Cholesky, and then model the gamma I inverse as the Cholesky of of process-based stuff. So in other words, basically you look at the Cholesky decomposition of a covariance matrix coming from a covariance function, and then form the gamma I inverses using the Cholesky of a Gaussian process covariance matrix, and then simply construct the CIJs. So that way, you can get the Q like this, and everything is valid. The CIJs are like this, and you get a valid model out of this guy, a Gaussian model, in fact. Which satisfies the fact that the realizations of the process over any finite set at node I is conditionally independent of the realization at node J, given everything else over that finite location in the domain. Okay, and this implies that the ijth block of the Q matrix is in fact 0, which comes from this particular construction here, the indicator of I not equal to J. Okay, however, this can be generalized because it doesn't really retain the marginal distributions from the covariance matrix, and furthermore, it ensures conditional independence only over a fixed finite set of locations. If we want to go to arbitrary locations where we want to use a predictive model as well, then we want to look at the conditional independence of random sets condition on everything else. And for those of you who like to think about these sorts of abstractions, I recommend a paper by Dalhouse, which is very nice. But you can also look at our recent paper in Biometrica. It's in print here. Again, you can click the link to get to the paper, where we have formulated what it means for two processes to be conditional independent given everything else, and construct what is called a graphical Gaussian process that will represent the two processes being conditional independent given all the other processes. All right, I'm not going to get into the details of this, but I'm happy to discuss this later on if anyone wants to talk about it. I'm going to skip this slide in the interest of time because I'm really running late and I do want to open some stuff. But the idea is to actually take a look at what is called like a strong product of graphs. You take two graphs, one over the space of locations, another over the space of variables. Use the strong product of the graph to construct an overall graph on the Cartesian product of two graphs, and then basically use a very familiar technique of Dempster's 1972 biometrics landmark paper on covariance selection to make sure that you actually build a spatial covariance structure retaining the properties of a given covariance or cross covariance matrix, so all the relationships are valid. And then over from that finite set where you do covariance selection, you go to an infinite set or uncountable set or arbitrary locations using something like a predictive process that can relate a finite dimensional realization to the arbitrary space. There is so this is the strong visual representation of the strong product graph. You have 4 random fields and you have 3 locations in each random field, and you're basically trying to build a whole graph by an algorithm that we call stitching. And you basically get a whole graph on this, and you model this in a way that the conditional independence relationships among these processes are retained while actually delivering predictive inference, estimation, everything from that multivariate model. Computational efficiency can be achieved using parallelizable chromatic Gibbs samplers, where you actually color nodes which have a common child, and then can be actually updated independently of each other. And similarly, you will have cross correlation parameters because it's a multivariate model now, right? So you would have parameters that are related to location 1, variable 1 and variable 5 within a location, as well as between locations. And you will have a graph that you will inherit from there. So chromatic Gibbs samplers that block update using conditional independent components become very, very computationally efficient. And I'm going to just quickly stop here by showing you that using these multivariate processes, even on a time series data, large time series data, could actually give comparable inference. Like here is a graphical Gaussian process as opposed to an autoregressive process. You actually get pretty similar root mean square errors. The coverage also comparable, prediction intervals covering most of them. But what you get out of this richness of these multivariate models is that you can actually introduce time-specific cross correlations and still estimate them in an identifiable manner. So that means if you have a space-time data where you want to just take the multivariate temporal realizations as unstructured, so just a covariance matrix there, but with a graphical structure coming from autoregression, you can still introduce much easily time-specific cross correlations and get comparable inference. Here are a set of references. I apologize if this is hopelessly biased in favor of my collaborators, but those are the papers that I've worked on, just in case you want to see what we have been doing. But this is not to say that others have not been working on it. There's some great work by William Kleiber and his collaborators on large multivariate data, including non-stationary modeling for sparse data using basis models. And then there's a brilliant paper by Matthias Gadsfuss and Joe Guinness, which is a general framework for these Vecchia processes that also appeared in Statistical Science. So there's a lot of that stuff. But if you're interested in the NNGP, then these three papers right here, the two Datta papers, the second one being a spatial-temporal extension of the first, and the third one being more on an algorithm-based, Bayesian algorithm-based paper for efficient computing. So I think I'll stop there, and thank you so much. And I'm so sorry I went overboard a little bit. It was too exciting.
Thank you, Sudipto. First of all, I invite everyone to unmute their microphone, and let us give a round of applause to Sudipto for this very complete presentation.
Thank you. I'm very humbled.
If any of the attendees wish to ask any question, I mean, we have still time for a couple of questions. You can unmute yourself, or also if you may write the questions in the chat, we can read it for you.
While we are waiting for questions, I actually have a question to Sudipto.
Sure.
What about, there's a trend right now in machine learning of using graph representation of spatial temporal data. So have you, that kind of relates to what you're talking about, graphical models?
Right.
Yeah. So essentially, you can create a graph out of your spatial temporal data based on how similar some locations are.
Right.
And then you can overcome the issue that you necessarily need to use just Euclidean distance. So have you looked at this?
Yeah, that's a great question. Thank you, Yulia. That is indeed a very, very relevant question. And so if I may just take this opportunity to look at this slide. So one way to think about the spatial temporal would be to simply look at this W1, 1, 2, 3, and 4 being time points. Mm-hmm. And you can still apply a graph, a general graph representation of the temporal process across these processes. They could be different type, like the autoregression would actually generate a particular type of graph. But if you could even do more general temporal representations, or rather I should say graphical representations of a temporal evolution, and you can use this stitching algorithm to build that. So in other words, you would now have two graphs, one graph that connects the dependence across time, another graph that connects the dependence among the locations within a random field. And then what you do is you look at the strong product of graphs. Here's a link to that, but I'll very briefly tell you what it is. Essentially, if you have, for example, the same location, like you'd label this as 1, 1, and label this black one as 1, as 2, 1, right? Well, then as long as there is an edge that relates the 1 and 2, the first time point and the second time point, this edge will be retained in the stitched graph. If you have something like 1, 1, and let's say 2, 2 for this black one here, for example, well, then you will have to see if 1 and 2 are related, and the location between this and this, within these two locations are neighbors, then yes, you will also have an edge right here. But both have to be satisfied. So I don't know if you can, if you click here from the strong product of graphs, you will see that the condition for adjacencies are very explicit. Basically, the first, so this is a strong product, means that each node will be like a point, right?
Yeah,
and that
right.
point, the first coordinate of that point has to be a neighbor, and the second coordinate of that point has to be a neighbor.
I see. I see. So it's based on, yeah, it's the nature is from
right.
Yeah,
and if you look at our paper here, there is a very specific example, although this paper is primarily, I would say, more on the theoretical side, because we spend a lot of time in trying to do this construction and showing that this is a valid process. But there is an example where we actually look at an autoregressive time series data, and and we try to do a graphical fit a GGP to that, and we get very you know, I would say comparable inference, as I showed you very briefly here, but with a slightly, perhaps in some cases, richer inference, like time varying cross correlations and so on.
Yeah, but it's but what I suspect is that, okay, so here you base everything is based on correlation, and you use, because you develop inference, so you do it through Gaussian processes, but actually it can go even beyond that, because the thing is that you can have features, and you can, for example, look at similarity, not necessarily in terms of a second moment, but of course you won't have as beautiful inference.
That is correct. That is correct. No, that's a very good point.
Applicable. Yeah,
that's an excellent point indeed. I have not looked at that personally yet, but I think that is something that certainly, as you said, you know, some folks are starting to look more and more into graphical representations, and I believe the machine learning community is also pretty active.
I can send you a few papers, because
it will be wonderful to take a look at it. I will just say that for the GGP to work, all you need is like a graph, either like this or like this, where each node is a spatial process, or some kind of a stochastic process. And then you can build a full stochastic process, which will satisfy the conditional independence relations from this graph about the processes.
No, I mean, I understand there is a beauty in your approach, because you can actually have a formal statistical inference.
Absolutely. I totally agree.
Yeah, if you look at something like some other similarity function, which may not even necessarily be distance, you would lose obviously this nice properties. But what I'm saying is that you can go beyond that. I mean, the whole idea is applicable way beyond of just Gaussian processes.
Right. Absolutely.
Yeah, thank you very much.
Yep.
Excellent. So I think that since there are no other questions, and for the sake of time, I think that we are going to stop right now. So many thanks to all participants for attending this TIES webinar. You may keep an eye in our website.
Can I thank you?
Oh, yeah, of course.
It's actually, I enjoyed the presentation. It's very comprehensive, and it's very nice to see you and to hear what you said. There is one point that I would like to raise, which is linking applications, real applications, to the theoretical development. If we are dealing with massive data set, 40 million or 50 million, there would be a requirement for 40 million questions to answer. And I think this is quite interesting if we can try to categorize the kind of applications in which these methods will be likely to be very effective and useful. And this is just what I wanted to say, just a comment. It's nothing more than whatever.
No, absolutely. Thank you. First of all, it's great to see you as well. And thank you so much for attending the lecture. If I may just take a second to respond, I completely agree with you. And that is why, you know, if I go back to the very first application here, only where you feel that there is a major inferential benefit, in our case, because we wanted to capture the structure as well as to give these predictive high resolution prediction maps, where we wanted to fit an entire space, rather a spatial random field to the entire domain, do we actually want to resort to these scalable models? In many cases, you can actually sample. I don't think good old sampling is going away. In many cases, depending upon the question, you can actually do sampling of big data and then, try to work with the sample. That is certainly not going away. And in many cases, that may totally be fine. But in particular for predictive inference over very large domains, or maybe when there are a large number of variables involved, and where the association among the variables can help improve predictive inference at unknown locations, especially when one variable is available at a location whereas the other is not, then there is some merit to looking at these complex scalable models.
Yes, I think it's quite interesting with what you have described, and I think there are lots of elements for people to work on. And I thank you, and it's nice to see you and see Julia and see everybody.
Thank you, thank you.
I just want to add, Sudipto, that the way how to address sampling, instead of doing random sampling,
right,
which will have some kind of caveat, of course, in terms of inference, you can actually select most important points. So again, so instead of, you can, of course, kind of embedded address it with uncertainty for random sampling, but in order to improve scalability, you can select the most important points and just use the surrounding points to kind of,
absolutely.
Yes. So that's
excellent idea. Absolutely. And I think you're absolutely right. Again, great point, and certainly, basically to broaden what you just said, if you want to do sampling instead of doing random sampling, you could actually perhaps do more structured sampling of some kind so that the spatial associations are retained or something.
So one way is start from a graph. Like you actually do use, you can use the network properties. So you start from a graph, you create a graph. And after that, you look at the most important points through network statistics. And that's how you select. And after that, you go through the rest of the analysis.
Yeah. There is a stochastic version of that too, by the way. In some ways, although it doesn't, at least the paper I know does not use graphical methods explicitly, is preferential sampling, right? That
that's right.
mentioned.
Yeah, that's right. That's the word this idea. Okay, thank you very much.
Thank you very much.
Thank you.
Thank you.
Thank you.